Have you ever wondered how a small piece of material, invisible inside your smartphone or charger, can control the direction of current like a one-way gate? That unassuming hero is the semiconductor diode, one of the most fundamental yet powerful inventions in the electronics revolution. Today, we're diving deep into the story, science, and applications of the semiconductor diode. From its roots in early 20th century physics to its role in cutting-edge quantum research. Whether you're a curious first-year engineering student or a seasoned electronics enthusiast, this journey will give you new insights into the most common non-linear component in your circuit toolbox. Our story begins in the early 1900s with a device that wasn't even electronic. It was called a crystal detector, used in early radios. A piece of galena, a naturally occurring semiconductor, was touched by a fine wire called a cat's whisker, and this setup allowed early experimenters to rectify radio signals. Then came the revolutionary moment in 1940, when Russell Ohl, working at Bell Labs, discovered the p-n junction. While examining silicon samples, he noticed that when light struck a cracked wafer, it produced a voltage. This was the accidental discovery of the junction diode. Just a few years later, this principle led to the development of the first practical semiconductor diode, a precursor to the transistor itself. From vacuum tubes to compact silicon chips, the diode helped shrink entire rooms of electronic equipment into the palm of your hand. Let's understand how this device works. At its heart, a diode is made from a p-n junction, which means it combines p-type and n-type semiconductors. The p-type region has an excess of holes, positive charge carriers, while the n-type region has an excess of electrons. When these two regions come together, electrons from the n side diffuse into the p side and recombine with holes. This creates a depletion region, a zone around the junction that acts like an insulator. It has no mobile charge carriers and instead contains immobile ions. Now comes the critical point, biasing the diode. If you apply a forward bias, positive voltage to the p side and negative to the n side, you reduce the width of the depletion region. This allows current to flow. If you apply a reverse bias, the depletion region widens and current is blocked, except for a tiny leakage current. This unidirectional behavior makes the diode a rectifier. It turns alternating current, AC, into direct current, DC, a job it does in almost every power supply. While the basic p-n junction diode is the star of the show, it has many cousins, each engineered for specific purposes. 1. Zener diode, designed to work in reverse bias beyond a specific breakdown voltage. It's used for voltage regulation. 2. Light emitting diode, LED. When forward biased, it emits photons due to electron-hole recombination, found in displays, indicators, and even medical instruments. 3. Schottky diode, made from a metal semiconductor junction. It has a low forward voltage drop and very fast switching. 4. Photodiode, converts light into current, used in solar cells, remote controls, and light sensors. 5. Tunnel diode, exhibits negative resistance due to quantum tunneling, used in microwave and high-frequency circuits. 6. Varactor diode, acts as a voltage-dependent capacitor, commonly used in RF design. 7. Pin diode, has an intrinsic layer between the P and N regions, useful in RF switching and photo detection. Each of these diodes is a unique solution to a specific problem. Proof of how versatile this component is. Understanding a diode also means understanding its I-V characteristics. In forward bias, current remains nearly zero until the threshold voltage, about 0.7 V for silicon, 0.3 V for germanium, is reached. Beyond that, current increases exponentially. In reverse bias, the diode blocks current until the breakdown voltage, where reverse current suddenly spikes. In Zener diodes, this behavior is deliberately exploited. This exponential I-V curve is what defines the nonlinear nature of diodes, something that engineers learn to design around and even harness. Now, let's explore where you encounter diodes in real life. Rectifiers. Full-wave and half-wave rectifiers convert AC to DC, found in chargers and power supplies. Clipping and clamping circuits. Shape voltage waveforms. Protect circuits from overvoltage. Voltage multipliers. Used in CRTs and high-voltage devices. Signal demodulation. Diodes recover information from AM radio waves. Logic gates. In early computing, diodes formed logic gates in diode transistor logic, DTL. Freewheeling diodes protect inductive circuits from voltage spikes, commonly in motors and relays. A modern diode is made using wafer fabrication techniques. Let's briefly cover the process. Start with a high-purity silicon wafer. Use ion implantation or diffusion to dope regions with phosphorus, N-type, or boron, P-type. Employ photolithography to define tiny areas on the wafer. Add metal contacts and sometimes passivation layers. Dice the wafer into individual dies, package them, and test. Materials other than silicon, like gallium arsenide, GaAs, or silicon carbide, SiC, are used for specialized applications, especially in high-frequency and high-temperature environments. Diodes can fail for many reasons. Thermal runaway. Excess heat increases leakage current, causing even more heat. Reverse voltage breakdown. Surpassing rated voltage can cause permanent damage. Overcurrent. Exceeding current ratings burns out the junction. To protect diodes, engineers use snubber circuits, heat sinks, and fuses. Understanding these failure modes is key for designing robust electronics. When analyzing circuits, diodes can be modeled in various ways. Ideal diode model. Assume zero voltage drop and infinite resistance in reverse. Piecewise linear. Model adds forward voltage drop. 0.7 V and reverse breakdown. Schottky diode equation describes current as I0, E minus KT 1. These models help simulate real-world behavior in software like SPICE. Used by circuit designers globally, even after decades of use, diode research is still alive. Quantum diodes and single photon detectors are pushing the frontiers of quantum computing. Organic diodes, made of carbon-based materials, promise flexible and biodegradable electronics. Nanodiodes are fabricated at the molecular level for ultra-dense chips. Tunnel field effect diodes aim to reduce power consumption in low-voltage applications. In research labs, even the humble diode is evolving into something unrecognizably advanced. As we approach the era of the Internet of Things, wearables, and quantum networks, diodes will only become more crucial. Their efficiency in power conversion is vital for renewable energy systems. Their miniaturization is critical for implantable medical devices. Their ability to emit and detect light makes them the eyes and indicators of AI-driven machines. In other words, the semiconductor diode isn't just a relic of analog times. It's the foundational building block of the future. So, the next time you see a tiny diode symbol on a circuit schematic, or find one glowing faintly on your motherboard, remember the rich world behind it. From quantum physics to smartphone screens, from power plants to spacecraft, the diode is everywhere. And while it may seem like just another chapter in your BTech syllabus, it's actually a window into the fundamental dance of electrons that powers our modern world. Thanks for watching, and if you want more deep dives like this, subscribe, share, and keep the curiosity flowing.